Welcome to Radio Signals. My name is Mark, and my call sign is N9WIB. This is the Technician License Series, Lecture 5, and today we'll cover Ohm's Law, energy, and the concept of power. To start, we're going to review what voltage and current mean, and then we'll define resistance, and then get into Ohm's Law, and finally, we will end with the review of power and energy. If we remember from our previous lecture, electric current can be defined as the flow of electrons. And as we discovered, that electrons have charge. So electric current can also be defined as the flow of electric charge. It's analogous to the flow of water. And current is measured in amps, and 1 amp equals 1 coulomb per second. So that's 1 unit of charge per second. And of course, current is measured with a device called an ammeter. Voltage, on the other hand, can be defined and is analogous to more of a difference in pressure. Voltage is the difference in potential electrical energy between 2 points. Voltage can be defined as the volt with a capital V, or it can also be depicted as electromotive force, or EMF, and sometimes that is defined as a capital E. So you can use the capital letter E or the capital letter V interchangeably to define voltage or to represent voltage in an equation. The SI units of voltage are the joules per coulomb, and if we remember correctly from the previous lecture, 1 joule of energy is equal to lifting 1 apple 1 meter off the ground. And to be a little more technical, it's 101 grams or 102 grams lifting that amount of mass 1 meter off the ground. And remember, the joule is a unit of energy. Resistance is a new concept we're going to cover within this lecture. Resistance is fundamentally important to Ohm's Law, and it can be defined as the opposition to flow of electrons. To put it more simply, let's use your kitchen sink as an example. Let's say you fill up your brand new kitchen sink with water. So that water is going to be equivalent to the pressure. And if you open up the drain, that water is going to flow out of that sink into the plumbing system at a certain rate. And that rate is going to be defined as the current. But if your plumbing is brand new, there's going to be very little resistance to the flow of that water, and your sink will drain very quickly. If you live in a 200-year-old farmhouse, you may have the same style of sink and may contain the same volume of water, but if you open that drain, it's going to drain very, very slowly. The pipe diameter may be about the same, but over time, that pipe has been subject to the buildup of tons of deposits and crud, which will slow the flow of water out of the sink. So that's the same concept of resistance. Low resistance in a brand new house with brand new plumbing, and very high resistance in a 200-year-old farmhouse with plumbing that's been compromised and degraded over time. Everything has resistance. There is no perfect conductor known in nature at the time of the recording of this lecture, and resistance is measured in ohms. Resistance and conductance are opposites of each other. So resistance is the reciprocal of conductance. A good conductor exhibits very low resistance, and a poor conductor exhibits very high resistance. So most metals, such as copper, is an example of a good conductor, and copper has a very low resistance. However, if you tried to pass an electric current through a piece of rubber per se, and it has very high resistance. That's why rubber and plastics are known as good insulators and not good conductors. So more examples of good conductors which have low resistance: copper, aluminum, and most metals. This is why we utilize these compounds in electrical circuits, because they conduct electricity well. Poor conductors have high resistance, and examples again include rubber, plastic, and let's say wood. So let's start reviewing some practical examples. We'll start by measuring the resistance of the human body. So this is a digital multimeter known as a DMM, and you can see that we have the setting on ohms. So it's going to act as an ohm meter and measure resistance. As we can see, we have it set in the highest setting of 20 mega ohms, and I've placed the probes between my two fingers, which are not connected except through the remainder of my body. And we can see that the resistance is quite high. It's 8.9 mega ohms. And if you remember back to the first few lectures, that's 8.9 times 10 to the 6th ohms. That's a very large resistance. However, that resistance can change. If I ran a marathon and started sweating a lot, that resistance would be significantly lower. I would not want to step barefoot in some seawater after running a marathon and then touch a power line. That resistance would be extremely low and extremely deadly. Next, I've made up a solution of, actually this is just plain old well water from the faucet. So the resistance of water here in this situation is 136 kiloohms, or 136 times 10 to the third ohms. In this situation, I've taken that same glass of water, but added regular table salt and dissolved it as much as I could. So the table salt dissolved into sodium and chloride ions, and the resistance is much lower. So the resistance is currently 14.3 kiloohms, or 14.3 times 10 to the third ohms. So salt water is more conductive than well water. Salt water has less resistance. Don't drop your radio or any other electrical device in salt water. Next, this is a device known as a resistor, and we'll get into components in the next lecture. But this is what provides resistance in electrical circuitry. In this case, it's a 1 kiloohm resistor, and the multimeter is reading 0.979 kiloohms. So we can safely round this off to 1 kiloohm. And in the last practical example, I've taken the two probes from the multimeter and attached it to a common wire we'd use to wire up a circuit on a breadboard. You can see that the resistance is not zero. So remember what I said before. There is no perfect conductor. This wire, no matter how short it is, still has some degree of resistance. And that resistance here is 1.7 ohms. So let's take a little bit of a deeper dive into resistance. The following formula lets us understand resistance to a greater extent. This is not required for your technician exam, but will provide you with a much greater understanding of the concept of resistance, both for your ham radio career and for your career in electronics as a hobbyist or even beyond. So as we can see here, resistance is equal to something called rho, and rho is a constant. It's the resistivity, and the units are ohm meters. This is multiplied by the length over the cross-sectional area. And the length is the length of whatever you're measuring, whatever resistance you're measuring. Most commonly, it's going to be a wire, and that length is going to be in meters. And the cross-sectional area is going to be of that wire in meters squared. So resistance is equal to the resistivity in ohm meters multiplied by the length in meters divided by the cross-sectional area in square meters. So if we actually try to understand the equation a little bit better, we can see that the resistance is going to go up significantly for longer wires. And it's also going to go up significantly if the diameter of that wire is smaller. So the longer the wire, the greater the resistance. The smaller the diameter of the wire, the greater the resistance. A shorter wire will have less of a resistance, and the bigger diameter of wire or the fatter the wire means less resistance. Now these are a few examples of the resistivity constant named rho. So copper has a resistivity constant of 1.68 times 10 to the negative eighth. That's a very small number. So you can see if we use rho and utilize that in the equation, the resistance we're going to get from the resistance equation is going to be very low. Aluminum has also a fairly low resistivity constant, or rho, of 2.82 times 10 to the negative eighth. But you can see that copper is a little bit of a better conductor than aluminum is. Next is seawater, which has a significantly different resistivity constant of 2 times 10 to the minus 1. So seawater is much less conductive than copper or aluminum and will have a much greater resistance than copper or aluminum. It will still conduct electricity, but not to the extent that copper or aluminum can. Deionized water is water that's free of all ions, so it doesn't have any dissolved calcium salts, sodium chloride, or anything else. So therefore, the ability to conduct electricity is really slowed down or hampered. And the resistivity constant here is 1.8 times 10 to the fifth power. Not negative fifth power, but 10 to the fifth power. So deionized water will have a fairly high resistance and low conductivity. Rubber, on the other hand, is several powers more resistant than deionized water. So rubber has a resistivity of 1 times 10 to the 13th, and that constant is very high in comparison to the rest. So rubber will be a very, very good insulator and a very poor conductor. So now we've come to what we've been looking forward to the whole lecture. This is Ohm's Law. Now that we've reviewed voltage, determined what current is, and defined resistance, we can define Ohm's Law. Ohm's Law is essentially voltage equals the current multiplied by the resistance. So we see that after we've defined what Ohm's Law is, we can obtain the voltage if we know the current and we know the resistance. What if we want to know the current and we had the values of the voltage and the resistance? So Ohm's Law can be rewritten in this fashion. So we're looking for current right here. So if we take the base equation, V equals IR, current multiplied by resistance, but we're actually looking for the current, we want to remove resistance from the right-hand side. So if we divide both sides by resistance, resistance will cancel out on the right-hand side of the equation, and we're going to be left with the current is equal to voltage divided by resistance. Same thing can be done for resistance. So what if we're looking for the resistance and we know the voltage and we know the current? Go back to Ohm's Law. But this time we want to know the resistance. So we want to divide the equation by current on both sides to get resistance by itself. So the current will cancel out on the right-hand side of the equation, and you're left with resistance equals voltage divided by the current. So you don't need to memorize 3 separate formulas. All you really need to memorize is Ohm's Law, voltage equals current multiplied by resistance, and you can derive the other values by simple algebraic manipulation of the equation. Okay, let's start doing some examples. So we'll start off with a simple example to try to determine the voltage across a 50 ohm resistor with a current of 0.05 amps. So the voltage is going to be equal to the current of 0.05 amps, and you're going to multiply that by 50 ohms for the resistance. And if we do our basic math correctly, we're going to come up with a value of 2.5 volts. So by knowing the current of 0.05 amps and a resistance value of 50 ohms, we determined that the voltage across that resistor is 2.5 volts. And let's go ahead and do another example. So we'll just divide the screen here. Same thing, VIR. But this time we're going to have a voltage. Now let's have a current of 0.002 amps. And we're going to multiply that by a resistance of 1,000 ohms. And if I didn't mention it, you can see the value. The symbol for ohms is an omega. So that's the ohm symbol right over here. That's the symbol for ohms. And if we do the math or put this into our calculator or just do it ourselves in our head, we see that this gives us a value of 2 volts. So with a 1,000 ohm resistor and a current of 0.002 amps, the voltage across that resistor will be 2 volts. Okay, this is going to be example number 2. So using Ohm's law again, but this time instead of voltage, we're going to want to solve for current. So remember what we did before. We just modified the same equation and we rewrote it for current. So as we know, current is going to be equal to the voltage divided by the resistance. So this time, let's say we have a voltage of 12 volts. And we have a resistance of 330 ohms. Remember that nice little Greek letter omega? Well, there it is again. So if we divide 12 volts by 330 ohms, we get a current value of 0.036 amps. So let's take another example. So same thing, same equation. We're going to solve for current. And let's keep the voltage the same. So voltage is going to be the same at 12 volts. But this time we're going to increase the resistance to a value of 1K or 1,000 ohms. So before you solve this, just think about it. So you have a constant voltage compared to the prior equation, the prior problem. Your resistance went from 330 ohms to 1,000 ohms. So your resistance is increasing. Is your current going to increase in the circuit or is it going to decrease? It's going to decrease. So with this equation and these values, you currently have a current of 0.12 amps. So with a smaller resistance, you have more current. You increase that resistance to 1,000 ohms from 330 ohms and maintain the same voltage, you have a smaller current. Okay, in example number 3, we're going to solve for resistance. So the first problem would be resistance over, resistance equals voltage over current. So that is the Ohm's law equation rewritten to solve for resistance. So this time we're going to have a voltage of 24 volts. And we're going to have a current value of 1 amp. So what resistance would that give us? So this is fairly straightforward and pretty simple. Don't even need a calculator for it. So 24 divided by 1 is 24 ohms. So with a voltage of 24 volts and 1 amp, you have a resistance value of 24 ohms. Let's try another one. So let's keep the voltage the same, 24 volts. But this time we're going to reduce the current. And we're going to cut it in half, in fact. So it's going to be 0.15, actually 0.5 amps. So 24 volts and half an amp. So we've kept the voltage the same, but we've decreased the current. So what's going to happen with the resistance? Is it going to go up or is it going to go down? So there's less current in the circuit. So if there's less current in the circuit, that means the resistance probably went up. And if we do the math, we see that it did. It went up to 48 ohms. Some people would say that resistance is futile, but I would not. So the final concept we're going to review in this presentation is that of power. Power is not energy. It is the rate at which electrical energy is transferred. Some people get confused with this concept and they think power is energy. It is the rate at which energy is transferred. And it is expressed in a unit called the watt. And the watt can be written with a capital W. So power equals voltage multiplied by current. So again, power in watts is equivalent to the voltage multiplied by the current. So if we break this up into the voltage and current's individual SI units, we can remember that voltage is an expression of energy per unit charge. So we're going back to the joule, or joules per unit charge, known as the coulomb. So a volt is joules per coulomb, and we're going to multiply that by the current. And as you remember, current is a rate of the flow of charge, or the rate of flow of electrons. And that's expressed as coulombs per second. So we can discover something kind of interesting here, that the coulombs will cancel out on the top and the bottom. So what you're left with are joules over coulombs. Power in watts is equal to joules per coulomb. And we can see this is not energy. Joules is a form of energy, is written as energy, but this is expressed as a rate because it's joules per second. So power is equal to the rate of change of energy, or the rate of transfer of energy. Okay, let's do some power calculation examples. So the power in watts in this example, so we're going to have a voltage of 13 volts. And we're going to multiply that by a current value of 3 amps. So what's the wattage of a device that is powered by a 13 volt source and is drawing a current of 3 amps? So that's going to be equivalent to 39 watts, or joules per second, because we know that this is a rate of energy transfer, right? Okay, in the second example, let's take a light bulb. So how many watts is this light bulb going to be utilizing? So power equals voltage multiplied by current, and we have a 120 volt source. And we have 1.5 amps running through the circuit. So that's going to be equivalent to 180 watts. So that's the rate of consumption. So that's the rate of energy transfer, joules per second, 180 watts. But let's do something different. So what if we ran that light bulb, we turned it on, and we ran it for 3 hours? So we have a 180 watt light bulb, and we multiply that by time. So for this, we're going to be using 540 watt hours of energy. So this is energy because it is no longer a rate. So we ran the light bulb for 3 hours and we consumed 540 watts. The equation above is the amount of energy used, but we ran that light bulb for 3 hours and we have 540 watt hours, not watts, but watt hours. Okay, now we're going to continue with some examples, but we're going to get a little more complicated. So let's still continue to work with power. So as we learned, power is equal to the current multiplied by the voltage. So this time we're going to have a current value, but we're not going to have the voltage. But we're going to have something different. We're going to have the resistance value. So how can we solve this? We don't have the voltage, but just go back to Ohm's Law. So we can actually use these two equations together. So Ohm's Law equals current multiplied by resistance. What we're missing here is voltage, right? But we see we have the current and we have the resistance, so we can actually substitute Ohm's Law into the power equation and get this. So power is going to equal to the current multiplied by the volts represented by Ohm's Law, which is equivalent to the current multiplied by the resistance. So we don't need the voltage because we can calculate the voltage. But something interesting happens here. So this equation can be reduced to the current squared, because you've got current multiplied by current multiplied by the resistance. So this is a very important concept. You can see that power is not a linear relationship when it comes to current and voltage. The current is squared. So you have essentially an exponential relationship. So the power is going to go up exponentially when you multiply it by current and voltage. So let's use that example. So what's the power value if we have a current of 0.5 amps? And remember, this is going to be squared, right? And we have a resistance value of, let's say, 100 ohms. So if we plug in our numbers and do the math, 0.5 squared is 0.25 times 100 ohms, and that's going to equal 25 watts. Okay, so you have 25 watts for a current of 0.5 amps, half an amp, multiplied by a resistance value of 100 ohms. So let's do the same thing. Let's keep the resistance constant, but instead of having half an amp, let's see what happens when we go to a full amp. So power is going to equal to I squared multiplied by the resistance, because we derived that equation here. Remember that? So power is going to equal 1 amp multiplied by 100 ohms. And we're going to make life simple. That amp is going to be squared, but it's still going to be 1, right? So power is going to equal 100 watts. So we doubled the current, but the power went up by a factor of 4 times. So power is an exponential relationship. Okay, last example, I promise. So we're going to do one more power calculation here. So power is going to equal the current multiplied by the voltage. And this time, let's keep a voltage of 12 volts. And let's say we know the resistance is 500 ohms. So for the power equation, we have the voltage right here, and we have resistance, but we don't have any current. So how do we get the current? And we go back to Ohm's law. So V equals IR, and if we're looking for current, you remember that we can rewrite Ohm's law as voltage over resistance. So that missing value of current is now right here. So that current is going to equal to voltage over resistance. So just to go back a little bit, so we saw voltage multiplied by voltage over resistance. You can see that this is going to be the same exponential relationship. So voltage squared over the value of resistance. So let's go ahead and plug the numbers in. So power in this case is voltage squared over resistance, and we have a voltage of 12 volts. And we want to square that, and we want to divide that by the resistance value of 500 ohms. And we can simplify this to 144 over 500, which will give us a value of 0.29 watts. Okay, so now you know how to use the power equation and Ohm's law together to solve for missing factors in one or the other equation. Okay, everybody, that about wraps it up for this lecture. And just to review very, very quickly, we covered Ohm's law, and Ohm's law states that voltage is equal to the current multiplied by the resistance. And we also delved into the power equation, and the power equation states that the power in watts is equal to the current multiplied by the voltage. And as you remember, power is a rate of energy usage, not just energy, it's energy usage over time. So that's about it. Have fun, and we'll see you at the next lecture. And don't forget that if you do like these lectures, please consider contributing on our Radio Signals website. You can go to that anytime and hit the Support Us button to find out more. Thanks.